Welcome. We are trying to calculate analytically the interfacial free energy for the free energy functional that we considered, and using Euler-Lagrange equation by trying to minimize that interfacial free energy, we arrived at this expression. And let us, so this AC squared 1 minus C squared is nothing but F0, and interfacial energy was nothing but integral F0 plus K dC by dx whole squared integrated over dx. Now, because the F0 is nothing but K dC by dx, so we can write it as 2 times F0 dx, right, and this integral goes from minus infinity to plus infinity. F0 is a function of C and the integral is over x, and the x integral is going from minus infinity to plus infinity. Of course, we know that as you go towards minus infinity and plus infinity, this term is going to give zeros, right. So, the integral is going to light up only in the interface region. So, we will change and the limits of integration and the integrand in terms of C, for example. Let us say that I want to replace dx by C and the integration from C equal to 0 to 1, because the interface is like that. So, C equal to 0, C equal to 1. So, minus infinity, C is 0. So, let me do that 0 to 1, because at plus infinity it is 1. Now, F0 of C we know, that is A C squared into 1 minus C whole squared, and so the integral dx should be replaced by dc. So, how do we do that? We use the same thing. So, let me call this as F0, and here if you look at F0 by kappa is dc by dx whole squared. So, dc by dx is equal to F0 by kappa whole power half. So, dx is nothing but kappa by F0 whole power half dc. So, I can put this here. So, I write kappa by F0 whole power half dc. So, this is the integral we want to evaluate. So, F0 you take it inside this square root. So, it is F0 squared and 1 F0 cancels. So, you get this. So, the interfacial energy sigma to be this expression, sigma is equal to 2 times integral 0 to 1 F0 kappa by F0 whole power half dc, that is equal to 2 0 to 1, you take it F0 kappa whole power half dc, okay. And F0 we know is AC squared into 1 minus C whole squared. So, that becomes 2 integral 0 to 1 A kappa C squared into 1 minus C whole squared whole power half. Remember, A kappa whole power half we called as beta, sorry, A by kappa we called as beta. So, let us call this as some other constant, let me call that as gamma. So, that is equal to 2, the gamma is a constant, let me pull out 0 to 1 C into 1 minus C dc, right, where gamma is equal to A kappa whole power half. We can integrate. So, this is nothing but 2 gamma integral 0 to 1 C minus C squared integrated. So, if we integrate, so we get the interfacial energy to be this, sigma is equal to 2 gamma integral 0 to 1 C minus C squared dc, that is equal to 2 gamma, C is C squared by 2 minus C cube by 3, 0 and 1, that is equal to 2 gamma. So, it is 1 by 2 minus 1 by 3 and 0 when you substitute is 0. So, minus 0 minus 0 it is gone. So, let us take 2 here, gamma that gives 1 minus 2 by 3, that is equal to gamma by 3, that is the sigma. Remember, when we took kappa and A to be equal to 1, gamma is 1, so sigma is 1/3, that is what 0.3333 it gave. And when I took kappa to be 4, right, gamma, which is square root of kappa A, so that becomes twice as much, so we got sigma as 0.66. Okay. So, this is what we numerically obtained, and this is how we analytically show that this is the solution. Now, the interfacial energy is not the only thing, interfacial width is also determined by the same expression. So, let us look at that part. So, we derived this while deriving earlier, saying that F0 by kappa is dC by dx whole squared, which means dC by dx is equal to square root of F0 by kappa, right. So, what we want to do is that, so you have this is the interface. So, let us take the central point and evaluate dC by dx, right, that will give the slope of this curve at that point, and you extend it wherever it cuts 0 and wherever it cuts 1. This distance is what is defined as the width of the interface. So, from here it is clear that the width of the interface goes as square root of, sorry, this is so the dC by dx goes as A by kappa in terms of the parameters that we are using, and we have already seen that sigma goes as square root of A kappa. Okay. This is consistent with our understanding, because when kappa is small, then the interface will be wider, because the cost associated with this is small. On the other hand, when kappa is when A is very high, that means that the barrier it has to overcome is very high. So, it is going to contribute more to the interfacial energy, and if the interfacial energy is high, then the width will also be high, because it wants to support so much of the gradient. Okay. So, in other words, with respect to A, both width and interfacial energy go as directly proportional, whereas with respect to kappa, where the interfacial energy goes directly proportional to power half, width goes as inversely proportional to power half. So, this is what analytical solution. So, all this is obtained for 1D, all this is obtained for a very specific case where we assumed F0 to have a specific form. However, it is it can be shown, and it is done by Kahn and Hilliard in their very first paper, that it is not necessary that we have to assume. Why is that? So, let us look at the F, which is F0 of C plus k dC by dx whole squared, and this is F by whatever NV, this is NV. So, integral F dx, and let us say that we do not assume anything for F0 of C, let us say that it is some function like that. Okay. So, the sigma, which is this minus, so it will be F minus C and mu b C beta minus 1 minus C alpha mu a, right. So, that is what. So, what is this? This is nothing but this line. So, if we define this difference of this region with respect to the common tangent as del f, we get the expression of sigma as nothing but del f, because f 0 minus this is basically del f plus k dc by dx whole square dx. Now, you can try to minimize this function and everything else follows in the same way. Of course, while trying to find a solution, in our case we had an explicit form for that this part which is ac squared into 1 minus c whole squared. So, I could take square root and call that as c into 1 minus c. So, we could get the solution. In the other case, of course, they do it by inspection, they realize that del f is 0 here, only in between it is going to take values and it should go with slope 0. So, they identify the tan hyperbolic as the solution, and it is generally known, this method is known as a tan hyperbolic method of finding solutions for nonlinear ODEs. So, most of them, I mean nonlinear PDEs also in one dimensions, you can write many of these nonlinear equations and you can write the solution as some form of tan hyperbolic. We will ourselves later see in the next lecture that we are going to look at the so called Allen-Kohn equation, which is another nonlinear diffusion equation, for which also the solution happens to be of the form of tan hyperbolic. So, in the next part I want to go back to the code that we wrote for calculating the interfacial energy, and I want to show the analytical solution that we have derived on the numerical solution that we have obtained. So, let us superimpose and see that we are actually getting the analytical solution. So, we know for a given kappa and given A what the solution should look like. So, we can take different values, we can plot the analytical solution, we can plot the numerical solution and compare how they are turning out to be. Okay. So, which is what we will do in the next part of this lecture. Thank you.